Hello everyone, this is going to be hopefully a shorter video that does a couple of things. It wants to talk about some of the differences between a 2D and 3-dimensional simulation, because this will also talk about adaptive meshing, which is only available for 3-dimensional simulations, not for 2-dimensional ones. So first off, what we're going to look at here is on some level, fairly simple geometry. It's going to be a double wedge sort of problem. It is going to be 3-dimensional. So what we're going to do is go ahead and go into the 3D CAD so we can draft this, because it'll be easiest to do in 3D CAD. You could also just do this with cones, or being creative in with rotations and translations and with basic parts, but this is easier in 3D CAD. So I'm going to make a sketch on the XY plane. This is going to be the cross section of our double wedge. We are going to start with wedge number 1, wedge number 2. We're going to go ahead and just extend this domain vertically up. Extend the domain vertically over, down, and over. So this is the entirety of the domain in question. I'm going to drop down a couple of additional lines here for the purposes of defining some relationships that will help us manage what this looks like with some dimensions here. So I'm dropping vertical lines from the back corners of both of these wedges and horizontal lines to connect this with the bottom of the domain. The wedge itself is a double wedge here. We're going to set an angle for the first half. We'll call it 10 degrees and we'll call it theta 1. And we will also set an angle for this second one. We'll call it 8 degrees. Call this theta 2. Notice that this is the angle between the adjacent wedges, not the angle between the flat lower surface and the second wedge half. Let's see here. We're going to tell this that this is probably, let's go with like 0.3 meters. We'll call this H domain. Call this, we'll call it an even 1 meter. This is L domain. Then we're going to give this a length dimension. So we'll call this 0.1875. Call this L1. And call this 0.25. Call this L2. This domain is a little bit undersized for this, but not catastrophically so, I don't think. It's at least enough to get the point across. And what we're going to do here is make sure the leading edge of this wedge is at 0, 0. 0. And to enforce that, we're going to, on this point right here, I can select it, select this point. You'll apply a fixation constraint, which just says that it cannot move. I do believe everything is fully constrained at this point. Click OK and close out the sketch. And what I'm going to do is I'm just going to extrude this through some distance here. We're going to call it 0.375 meters. It's probably good enough here. And let's see. We can go ahead and rename these faces in 3D CAD. No, you can do this like the normal way with split by patch or split by angle on the parts level as well. This is somewhat easier on the 3D CAD level. It's slightly more robust to do it as soon as you possibly can. I already named the inlet. And I think that's probably everything. So we can close this. And we can say new geometry part from our 3D CAD Model 1. That should all be fine. And now we have a part, which is our body, which has all of our named surfaces. If I make a new geometry scene, we can see this. So one thing that might need refining here, so let's go in and edit this really fast, is I'm going to rename this one and rename this wedge 2. Close. If we right click this and say update, it will update and pull in our new wedge 1 and wedge 2. Notice they're not shown in the scene because when we made the scene, it didn't know that there was anything called that and it didn't include them as a result. I'm just going to go back and select everything. Okay. So we have all of our named surfaces. Now we're going to go ahead and say assign parts to region. So you can see, create a region for each part, create a region for each part surface, apply, and this has created a region with all of our surfaces. We're going to go ahead and set some boundary conditions here. The first one is going to be, well, the wedge is just a wall, that's fine. The top and outlet are going to be pressure outlets. Inlet is going to be a free stream inlet. The bottom is going to be a symmetry plane, as well as left and right. So what this acts like is that this is a wedge where the same exact thing is mirrored below it. That is the flow on both sides of these surfaces. Sorry. If we look on this surface right here, the flow on the top of it and the bottom of it would look identical, as if this were a sharp edge wedge rather than a half wedge like we have it modeled here. So we won't have a boundary layer on these surfaces. No flow will be allowed to move through them, but they will act as a boundary for the purposes of the simulation. So for the mesh, here's where things get a little bit different. We don't need to badge for 2D meshing anymore. This is no longer a 2D mesh. Instead, we have an automated mesh. As usual, we select the body we want to mesh, surface remesher, trimmed cell mesher, prism layer mesher. And we need to set all the same things: target sizes, base size, minimum size, etc. So I'm going to set this to 1 centimeter. The number of prism layers, we're going to up this to 8. Surface growth rate, we're going to set to a user specified nice and slow 5%. The volume growth rate, we're going to set to very slow. Prism layer total thickness, I'm going to leave that at 1/3. Let's see here, anything else that needs to be changed? The minimum size, let's go ahead and knock this down to 5% instead of... Oh, sorry, that's 0.05%, so 5%. There we go. So it'll let it be down to a minimum size of 0.5 millimeter. The target size... There we go. Turn on the highlighter to make it easier to see. The target size is 1 centimeter. The base size is 1 centimeter. The minimum size is 5% of the base size, so 1/2 of a millimeter. Our volume growth rate got set to very slow. Our maximum cell size, I'm going to make this 800%. So no cell will be bigger than 8 centimeters to a side. And I'm going to go ahead and make a surface control. And this will pretty much be the only surface control. You could get really fancy with this, but we're going to let the computer do the work for us, as finding where the cells need to be refined or not. The only thing we're really going to do is tell it where we want big cells. So we're going to tell it that out here by the boundaries, we want cells to be about 8 centimeters to the side. And we also do not want it to use prism layers. Let's see what this mesh looks like. This is what our mesh looks like. Not the most glamorous mesh in the world, that's for sure. But it's a baseline to kind of start with. So, let's go ahead and select our continua here. This will be a supersonic simulation. So I'm going to select coupled flow. You might be able to get away with segregated flow depending on how fast you're doing it, but I'm going to select coupled flow. Turbulent, K omega, ideal gas. But we're going to select adaptive mesh for the optional models. This is going to do a couple of different things here, but it will mostly include an adaptive mesh node here. I'll get to this in a second, but let's set some boundary conditions first. Most of these don't actually require boundary conditions. Inlet does. We want to tell it how fast is our flow going. I'm going to say Mach 2.3. The static temperature, static pressure, and really that's it. So we'll leave all that default except for the Mach number. The Mach number we cranked up to 0.3. And let's see. We pull up a scalar Mach number scene. See what this looks like. Scalar. Mach number. And we want to plot our symmetry planes for sure. I'm running this. So part of the thing is that we know the shockwave should be relatively narrow, but it's drawing just big old fat lines down here. That's not great. Actually, hold on. I need to tweak our geometry a little bit. I may have, let's see here. Turn down theta 1 and turn up theta 2. State, execute. The 2 needs to be higher still. Anyways, that's wow. Tell you what, let me make this longer. 0.5. We'll make the entire domain longer to help compensate for that. The height of the domain will also crank up to 0.5. We'll just make everything a little bit larger. There we go. Okay, this is definitely going to do what I want. AKA, well, in this case, it has a complex shock-shock interaction here that is very clearly not behaving very much like a shockwave. You know, shockwaves from fundamental aerodynamics should be very thin lines with sudden discontinuities in properties across them. We do see a discontinuity, but it's not a very thin line. It's restricted by the size of these cells. So how do we get it to automatically resize these cells? How do we get it to automatically adaptively refine the mesh so the cells are only large where it needs to be? And to do that, we need to utilize this adaptive mesh node. So under adaptive mesh, there's some settings here. These are probably okay by default, except for maybe this one to limit the cell size. We probably don't want cells to get too small. So I'm going to limit them to 1e to the negative, or I'm going to limit it to 5e negative 5. That's like 1/20th of a millimeter. That's pretty small. And that's just checking the limit cell size and giving it a minimum size to use. But we need to define a criteria. Like, it's all well and good. We can ask the computer to adaptively refine our mesh, but how does it know where to refine it? You need to tell it. You need to tell it what criteria to use. So I right click on adaptive mesh, said new user defined mesh adaptation. This lets us, user, define how we want to adaptively refine the mesh. The first level just has a couple things, is do you want to enable it or not? How many times consecutively do you want it to let the computer make cells smaller? I'm going to increase this to 4 so it can make cells smaller in up to 4 steps. Depending on how good your refinement is, it might not need that many steps, but it's allowed to use up to 4. And you can also allow it to use the refinement when it's initializing the solution. I don't think we particularly need that for today, but I'm gonna leave it off one way or the other. So now we get into what's a little bit fancy here. That we need to tell it how to define when a cell needs to be bigger, how to define when a cell can be allowed to be smaller. Now, when I say a cell is allowed to be smaller, what I mean is it will never make a cell sorry. I need to know when it will let a cell be larger and when a cell will be smaller. It will never make a cell larger than the way it started. It will only make cells smaller than when they started. But if it refines a cell, it makes it smaller. It iterates a few times and realizes, oh, hey, this cell didn't actually need to be small after all. It can roll back that change and make the cell big again. So this takes a couple of things, but we're going to first look at the scalar function. This is a scalar function, the value of which the simulation will check for every cell. And it will say, okay, is this above this range? Make the cells smaller. If it's above the maximum of this range right here, make the cell smaller, refine it. If it's inside of this range, don't change it at all. Keep it the same size. If it's between 0.2 and 0.8, don't change the cell. If it's below 0.2, make the cell bigger. But we need a field function to look at. You can't just pick pressure because you can have big cells and big values of pressure. We need to create a field function that looks at not just a value we care about, but also a combination of that and the size of the cell. So I'm going to make down in tools under field functions, I'm going to make a new scalar field function that we define. I'm going to call it a refine function. Name this appropriately. A refine function. It is a scalar dimensionless function. We are going to create a definition for it. So what I'm going to look at is the magnitude of the gradient of Mach number. What is a gradient? It's the direction and the magnitude of the rate of change of a quantity in space. How rapidly is this quantity changing with distance, and in what direction is that change maximized? So a gradient has a magnitude and a direction. It's a vector quantity. So I'm going to ask for the magnitude of a vector quantity that is the gradient of Mach number. And what I'm going to do is I'm going to multiply this by a quantity called adaptation cell size. This is going to take the size of the cell and multiply it by this value. So the smaller the cell, the smaller the value. This is going to kind of be a self-limiting artifact on the cell size, where it won't kind of just infinitely make the cells smaller, or it won't just try and make them as small as it possibly can. Theoretically, it can find a sweet spot in the middle where the cells are an appropriate size. But what the heck is a good value for this? Like, I don't know if 0.2, 0.8, I don't know if 2, 10, 20, 100 is a reasonable value for this. We could run it and just see what it does. That might tell us. Or we can just turn off this mesh refinement for the moment and run this a little bit. It's already run out to iteration 800. It's actually very stable. So let's look at, with a scalar scene, what is the value of this field function that we're looking at here? Well, it's not 43. That's pretty clear. If I limit this to 0 to 2, this implies that the value is probably more like, I don't know, even less than 2, honestly. Like 1. So, honestly, anything that's more than about 0.125 looks like it can be refined. Everything that's between probably 0.12, like, okay, so I'm going to call the cutoff here for the coarsen and probably 0.125 for the refine. Let's go back to adaptive mesh for a second, and we can say, hey, at the lower end, 0.125, the upper end, 0.25, and enable it. So we want to be able to see the mesh changes. So let me go ahead and pull up the scalar scene, scalar 1 displayer, and display the mesh. We can see what the mesh looks like. Initialize and hit. Look, it's making these cells dynamically smaller as it needs to in order to get a better idea of where these prism layers are. Now, this is definitely not quite 100% hard and fast. You need to do generally quite a lot of experimentation, I would think, to figure out what's an appropriate value for these refinement ranges. I think this is actually way too small. 0.25 and like 0.75 might be more appropriate. But if we just look at this, we can see very clearly that cells are being refined. Cells are being made smaller. And theoretically, this should change depending on how strong these shock waves are. So let me just stop this for a second, hit save. And I'm going to change theta 1 from a benign 8 degrees up to a somewhat ridiculous like 18 degrees. And theta 2 can honestly just stay at 12. So I'm going to tell it to remesh. It did a whole bunch of rearrangement here, and I'm going to tell it to run again. It's going to figure out where these new shockwaves are. You see it actually moving them for starters and then making the cells out there smaller as it gets a better idea of where this shockwave is forming. Now, some of these cells are still pretty big. So arguably our value is probably a little bit aggressive. You need to turn down the upper end of this and say like 0.25 to 0.5 might be more appropriate. We could also look at other field functions and see what do they potentially look like as well. But that's sort of creativity, and you'd have to look at, okay, based on how I would make this mesh, if I know exactly where this shockwave is already, here's where I would make it fine. Here's where I would make it coarse. And then go look at field functions. Usually it takes cell size into account to estimate, okay, how can I give the simulation a criteria that it can figure out where cells need to be coarse, where cells need to be fine. So I can, oh, it's going to pretty much immediately stop running. So let me turn off my stopping criteria very quickly here. It's no longer going to stop at 1,000 steps. And let it continue. It appears to be doing a reasonably good job of figuring out where those shockwaves are. At least the first shockwave and the interacting shockwave. it's not doing such a great job about this secondary shockwave, but this is a relatively weak shockwave. So this is adaptive meshing where it's again figuring out where these cells need to be big, where they need to be small. I can change this Mach number, my boundary condition. We go ahead and just change this Mach number to something a little bit more benign. We'll do like 1/8 instead of 2.3. And hit run. And it'll take some iterations to figure this out. You can kind of see that lower Mach, or at least the gradient, slowly working its way in there. And then we should shortly see it start to figure out that, hey, this shockwave is at a different place. And it's going to adjust the angle appropriately. We're just going to let this run for a minute and see what it does. Oh, yep, that shockwave is definitely, according to it, moving forward. So I think by default it's doing this adaptive meshing every 5 iterations, which is probably a bit aggressive. Oh, it's not actually up here. Down here in solvers, there's an adaptive mesh node, and it's set to trigger every 5 iterations. I'm gonna tell it every 25 instead. Not remeshing quite as often. According to this, it's starting to think it's like a detached bow shock almost. I wonder why it's thinking that. But in any case, it's again adapting the mesh only where it thinks it needs to, and there's now no refinement. The cells aren't even all that small. Out here where they used to be quite small. So that's adaptive meshing in a nutshell. You can apply it to anything. Literally anything you can apply it to. That's three-dimensional, I should say, in STAR-CCM. However, some things don't warrant it. Really, it's only very useful when you either A, don't know where you expect cells need refinement, or B, you expect which cells need refinement to change rapidly and regularly during the simulation. Those are really the two use cases. If you don't fit in one of those cases, it probably doesn't make sense to use an adaptive mesh. So we'll keep the assignment for this one basic because we're sneaking up towards the semester here. But this is a crash course in adaptive meshing. Again, to review, it's a physics continuum thing. It's an optional model you select adaptive meshing. You get to define a new user-defined mesh adaptation criteria where we can enable or disable it. We control how many times it's allowed to refine the mesh. And then we tell it, what is the criteria? Based on this value, when should I increase the size of the mesh? When should I decrease the size of the mesh? When should I leave the mesh alone? And we, in this particular case, are looking at the magnitude of the gradient of Mach number multiplied by the cell size. What we're looking at. Both literally, that is this field function we're looking at right here on this scene, and it is exactly what the adaptive mesh looks for. It says, hey, is this value less than 0.25? Make the cell bigger if it is. Hey, is this value more than 0.5? Make the cell smaller if it can, if it's allowed to. hey, I'm in between these ranges. Don't do anything. Keep the current size. Um, and yeah, that's pretty much it. So we're going to go ahead and just wrap this up here for the moment. We'll talk about this in lecture quite clearly, but that is a crash course in adaptive mesh.